Hey, what's going on, guys? Coming again here. In this video we're going to learn how to convert x86 assembly to x86 machine codes, and we're going to have a look at the jump command in particular. So we're going to be dealing with three types of jump commands. So conditional jump, short one, conditional jump, unconditional jump, short one as well, and far jump, which would be the direct one. So difference is that the short jumps, either non-conditional or conditional, dealing with the relative 8-bit offsets. I will now explain what exactly that means. And when it deals with the far jump, so in the real mode, in order to jump between the segments, we can use far jumps, just for instance, to interact between different apps. And in this case, we're going to be using the actual address of where to jump. So I hope that's clear. And the very first instruction to deal with is this jump equals and then the label. So we want to jump here. However, from the machine codes perspective, there is no such thing as label or variable or whatever like that. It's just a matter of either absolute address or the relative offset. So in our case, this is the matter of the relative offset. But first, we need to get the proper operation code or opcode for this jump equals. So this is the conditional jump. So the general formatting for conditional jump is going to look like this, and we can just paste it in here. Now the TTTN is what in particular we want to do. So what kind of condition are we dealing with? So it literally encodes the conditions, and we have this jump equals, which is going to be 0, 1, 0, 0. Copy, and now we can replace TTTN with this one. And now how to calculate this 8-bit displacement. So when we encounter 8 bits, so now it's clear why the nope operation is here. It just serves as a placeholder to calculate this relative offset. Okay, so 1 byte, okay, 1 byte instruction. So 1 byte, 1, 2, 3, 4, 5, 6, 7, and then jump itself would take 2 bytes or 16 bits. So I hope that's clear. You will see why exactly. So when we encode this one, you'll see that jump takes exactly 2 bytes. Okay, so let's actually calculate our displacement. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this is in decimal, but we need to convert that to hexadecimal. So if we have decimal and we have 19, and then we just convert this to hexadecimal, we got 13. And this is exactly the value. This is the exact offset we need in order to jump from here to this label. It doesn't matter that we don't compare anything, so it's not clear whether there's just jump equals fires or not. Most likely not. So this code doesn't really make that much sense from the actual assembly program, but it's just intended for the purposes of encoding instructions to this x86 machine codes. Okay, so 13 hexadecimal, and now it gets clear that we have up to 2 bytes to encode the jump command. So this is going to be 7 in hexadecimal, and this is going to be 4. So 7, 4, 13. And let's just have a look. Let's verify ourselves with NASM assembly, and here we have exactly the code that we're looking for. So 7, 7, 4, 13. But now let's say we want to say jump greater equals. So all we need to change is this TTTN, okay, this part. So we just go to jump greater equals, and we just take this one and just put it here, for instance. So this is gonna be D, right? This is gonna be D, so 7D 13. So if we have a recompile, like reassemble this, we have 7D 13. Okay, now let's say we want jump less. So in this case, we use C. Okay, this is C. Jump less. Okay, jump less save, and we got our 7C13. So I hope it's clear. So whatever condition you want, you just replace this 4 bits with the corresponding TTDN, kind of like with the corresponding TTDN value. Okay, so the next thing, yeah, we can keep it just like so. So let's now encode this jump command. So this is unconditional jump, and it has a different operation code. So this is the opcode for unconditional jump, so short jump, just a jump, not conditional. So we just grab this and go in here, back, and paste. And then we need this 8-bit displacement, just like we did previously. So it jumps to repeat. So this instruction would take 2 bytes. So just 2 bytes and 2, but we can do it like this. So byte should obviously be created of up to 2 digits in hexadecimal, right? So this is the value, and this is hexadecimal value. Now let's convert it to now let's convert all of this stuff to hexadecimal. So this is going to be E, and this B, I believe, B, E, B, and 0, 2. Okay, so let's assemble again and see what happens. So we have this 90 for no operation, which is self-explanatory, and then we have this EB02. So this is how we encode this jump. And now let's have a look at this one. So this unconditional jump is interesting because it goes to the negative direction, and this is where things are getting a little bit complicated, but no worries. I'll now demonstrate how easily this can be resolved. So we take absolutely the same operation code here, and now we need to calculate the offset exactly the same way as we did before. So 1, 2, 3, 4. Okay, so this is what we need to skip, subloop 1. Okay, so we have 0, 4 hexadecimal, but not that fast. So in order to deal with a negative value, we need to consider one additional step. So here we see the description that for positive displacement, just add bytes to the label, and for negative one, we need to invert bits and subtract 1. Okay, so this is how we do. And to make it a bit more easier, to make it easier, let's actually turn this 0,4 hexadecimal to binary format. So this would be, in order to invert bits, it's really easier to do in binary. So here we have 0,4 in binary format. And now invert the bits means all the zeros would turn to ones, all the ones would turn to 0. So we have 1, 1, 1, 1, and here 1, 0, 1, 1. And now we need to, from this value, we need to subtract 1. So here we will have 0 after. Okay, so this is it. And now we can just get rid of this sort of a thing and convert it to a hexadecimal. So we have E, then B, E, B, then F, okay, and 10, 10 would be A. Okay, so let's have a look whether it matches. So we have, yeah, here it is. So E, B, F, A, which is exactly the case. So we had EB02, now EB, F, F, A. Cool. Yeah, now let's go further on. Yeah, so here actually, yeah, we want, it's not an operation, I'm sorry. So here we again want to jump back to loop 1. So absolutely the same scenario here as well. So we just grab the operation code. And now let's calculate the displacement. So 1, 2, and we see that here we have 2 bytes. So 1, 2, 3, 3, oh man, 3, 4, okay, 5, 6, 7, 8. So 8, 8, but byte should the byte in hexadecimal should be composed of up to two digits, so 08 hexadecimal. Now, if we turn this to binary, this is gonna be like 00001000. So we convert it to hexadecimal. Now we need to invert the bits. So here we will have 1111, and here we'll have 0111. Okay, and the code is gonna be EB. So EB. Now this is gonna be F, and this is gonna be 7. Okay, and now let's see if it does match. So EBF6. I'm sorry guys, that's because I forgot to subtract 1. Obviously we need to subtract 1, hence we have F6. Yeah, obviously don't forget to subtract 1, that's very important. So EBF6, this is what we have. Okay, and yeah, probably one last thing left here is to deal with this direct jump to a far jump to a different memory segment. And in order to deal with this, here is how this is done. So first we need to grab the operation code, and here is the opcode, copy, and then the address. Okay, so in order to we can't so you like naturally what we could have done here is like say 05771234. Okay, but we need to bear in mind that this x86 processors have a little endian byte order, so we need to reverse it. So actually 34 goes first, okay, then goes 12, then goes 77, and finally this 05. So this value is little endian version of this two values in hexadecimal. So it would be better to say like hexadecimal like this and like this. Okay, so now all we need to do is to say, so this is going to be E, this is going to be A, okay, and then this value followed by this one, and that's pretty much all about it. So let's check this final instruction to make sure that we did everything properly. Okay, so EA, yeah, here it is, we go EA34127705. So this is how easily we can encode this kind of like far jumps. Okay guys, I think this is it from my side. Thanks for watching. Until the next time, and take care.